Okay, so in today's lecture, we will complete the discussion on the postulates of quantum mechanics, and we will discuss the fourth postulate that deals with the composite systems. And then we will go on to describe how we can use postulate 4 to construct composite states of qubits, and also how we can construct composite operators that act on multiple qubits. And then we will discuss a couple of important multi-qubit gates, especially 2-qubit gates. And the most important one is the control NOT gate. And we will see how we can use this gate to construct multi-particle states, especially entangled states. And then at the end, we will discuss an important concept, which is called the phase kickback. And it is used to implement general phase functions in various quantum algorithms that we will be studying next week. And then I will also have a lab session today that will describe how we can use multi-qubit gates, and how we can, build on the single qubit gates and circuits that we studied last time. Okay, so today I'm going to start experimenting with one node. So let me share my screen. Hopefully the glitches today are going to be smaller than yesterday. Okay, so I will share this notebook with all of you after the class, because I will have to find out emails from Zambil of all of you and then send you a sharing link. So let me make it full screen. Okay, perfect. So as I was saying, that today we will complete the discussion on the postulates of quantum mechanics. So today we will discuss postulate number 4. That deals with composite system. Composite quantum systems are composite, your multiple qubits. Okay, so this postulate states that if we have multiple quantum systems, let's say quantum system A, B, C, and so on, let's say up to Z, and we want to express their composite quantum state, then we can express it as a superposition of the states of type like this. Let's say psi1 of system A, and then tensor product of state of state psi2 of second system, suppose B, and so on, like this. In general, we will have these, subscripts written under these states that will tell me that okay, this is the state of this system B. And when you have given the subscript under them, then it doesn't matter where the position of the state is. If you remember, okay, for example, I can write it like this, but I have to write B here, and then psi1 A, and so on. However, what we can also do is, sorry, let me figure out how I can scroll down. Perhaps I'll have to exit. Okay, so here it is. So if I put these subscripts, then I don't care, where I write these states. It can come first and this can come later, etc. However, if we keep in our mind that, okay, the first system state is coming here, and then the second system state is coming over here, and so on, then we can, get away without writing any subscript. But in that case, we have to make sure that we fix this convention before and then follow it throughout. So this is how we can express the composite state of a system. Similarly, if we have multiple gates that are acting on the system, let's say gate X is acting on some qubit 1 and gate Y is acting on qubit 2 and so on, then we can write the composite gate of this whole system like this. So this X acts on first qubit and then Y acts on second qubit, and we know how we need to work out this tensor product. For example, this X is 0 1 1 0, and this Y is 0 minus iota 0, and then we have to work out the tensor product, like this 0 multiplies with all of them, and this 1 multiplies with all of them, and this 1 multiplies with all of them, and 0 multiplies with. So this matrix represents this composite 2-qubit gate. Okay, so this is how we can express these the states and the composite gates of multiple qubit systems. Let me now work out a couple of examples, because they can then be helpful in constructing more complicated states. For example, if I have only 2 qubits, let me specialize to 2 qubit systems right now, and similarly you can construct states for multi-qubits just following along these examples. So I have let's say qubit A and qubit B. So these are 2 physical systems. So their joint state can be expressed as superpositions of states like these. And as an example, let's say this qubit is in state 0, and this qubit is also in state 0. Then this joint state by the way, most of the time we don't even write this tensor product, and people just write 0 0. And when you see like 0 cat and cat 0 and cat 0 written just side by side without any thing inside, it actually means that this is a tensor product. And some people are actually even lazier, and we are also going to be lazy, and we wouldn't even be bothering with the writing 2 cats. We will just write 0 0 like this. So this is cat 0 0. So essentially it means that qubit A is in 0 state and qubit B is in 0 state. Similarly, if you have 3 qubits, you can write the state after that as well. But let me warn you one thing, that some people have opposite convention. For example, if this is a qubit with state 0 and this is a qubit with state 1, some people would write it as 0 1, and some people would write it as 1 0. That they may be writing this last one over here and this first one on the right side, and some people would write this first one on left and the last one on the right. So there are these different conventions. What I'm going to do in this course is if there are qubits like first, second, third, and so on. So my first qubit would be here first, and then the next qubit, and so on. Anyway, so let's work out this state 0 0 in matrix form. So the state of the first qubit is 1 0, and then tensor 1 0. So this is nothing but 1. So this 1 multiplies with 1 0, and I get 1 0, and then 0 multiplies with 1 0. So this is 1 0 0. So it means that this 0, 0 state can be written as this 1, 0, 0 column vector. Similarly, if I have 0, 1 state, this is 1, 0 tensor 0, 1. This can be written as 0, 1, 0, 0. And if we have 1, 0 state, you can check it out yourself. This is this. And similarly, 1, 1 state is 0, 0, 0, 1. Now, these are not the most general states that these two qubit systems can have. Even though, if you think about these qubit systems as classical, systems, we would think, okay, one qubit is in a certain state, another qubit is in a certain state, and we should always be able to write the state of the whole system as the state of one qubit tensor state of the second qubit. But there are other states that are allowed by quantum physics, which are the superposition states of this joint, two qubit system, which means that I can have a state of this two qubit system, which is actually the superpositions of these canonical state. For example, my system could be in iota 0, iota 1, 1 over square root 3 state. And if this, you can easily see that this can be written as 1 over square root 3 iota. Actually, let me write it like this: iota 1, 0, 0, 0 plus 0 into 0, 1, 0, 0 plus iota into 0, 0, 1, 0 plus 1 into 0, 0, 0, 1. Which means that this state psi is 1 over square root 3. So this 1, 0, 0 is nothing but 0, 0. This 0, 1, 0, 0 is coming with 0, so I don't have to write it. And the next term is iota 1, 0, and the last term is 1, 1. So this state is a joint state of these two composite, these two qubits. And I can't, write it as a product of one state and another state. So these types of states, which cannot be written as tensor products of some state of qubit 1 and another state of qubit 2, these are called entangled states. Okay, so it means that if you disturb qubit 1, the qubit 2 will also be disturbed, because qubit 1 and qubit 2, they are in a joint state that cannot be written as state of first qubit and state of second qubit. So this joint state of these two qubits, this is essentially one quantum system, so to say. And then qubit 1 is just a part of this bigger quantum system, and disturbing one disturbs the other. Okay, so to give you another example, let's say I have a state like this. By the way, you can easily now see that the states 0, 0, 0, 1, 1, 0, and 1, 1, they form a basis for these two qubit system, because any state can be written as a superposition of these basis states. Since in general the composite state has this four-dimensional column vector, so general column vector A, B, C, D can be written as a sum of these four states. So this is one basis of this two-level system, and this is usually called computational basis, again, simply because when we do measurements, they are done in terms of the 0 and 1s of individual qubit. So we have this basis. This is computational basis of two qubit system. Let's take a few more examples of a few other states. For example, if I have this plus plus state, that my qubit 1 is in plus state and my qubit 2 is in plus state, this is sometime written like this. Let's find their joint state. So this is nothing but 1 over under root 2, 0 plus 1 tensor 1 over under root 2, 0 plus 1, and 1 over under root 2, 1 over under root 2 is 1 over 2. So 0 into 0 is 0, 0, 0 into 1 is 0, 1, 1 into 0 is 1, 0, and 1 into 1 is 1 plus. Now you see, this is a state that looks like, okay, very complicated state, but this is still not an entangled state, because it can be written as the tensor product of plus state and another plus state. That we can, this is nothing but a way of saying, okay, qubit 1 is in plus state and qubit 2 is in plus state. So this is not entangled. Similarly, and by the way, if I write it in column form, this is 1, 1, 1, 1. You can work out the expression for plus minus, minus plus, and minus minus states. And I leave it to you to show that, first of all, these states are orthogonal, that if I have plus plus state here and I take its inner product with the plus minus, this is 0. If I take the inner product plus plus with minus plus, the answer is still 0. And similarly, the inner product of plus plus with minus minus is 0, and so on. So, and you can check that the magnitude of all of these states are 0. For example, this is plus plus. So if I find its magnitude is like 1 square plus 1 square plus 1 square plus 1 square is 4, and 1 over 2 whole square is 1 over 4. So 4 by 4 is 1. So they are normalized. So this is another basis. Plus plus, you can call it Hadamard basis. Plus minus, minus plus, minus minus. So this is another basis that can be used to represent states of 2 qubit systems. Any questions about these 2 qubit states?
सर सर आपने कहा था कि प्लस प्लस स्टेट में एंटेंगलमेंट नहीं हो रही, सर वो जरा फिर से बता दें.
Okay, because this is plus plus state, it means that this is by definition is a state where qubit 1 is in plus state and qubit 2 is in plus state. So when we can describe our system by using word and, that this qubit is in this state and the other qubit is in this state, it means they're not entangled, because we can describe them individually. When I took this example, this is an example of a system that you cannot describe, okay, what the first qubit is in and what the second qubit is in, because I cannot write it in a product form. Okay.
टेंसर प्रोडक्ट के फॉर्म में नहीं लिखा हुआ है, इसलिए आप कह रहे हैं.
So I cannot write it in as a tensor product of some 2 other states. वो जरूरी नहीं कि वो 0 0 हो. They can be, any other states, for example, 0 1 1 0, or any combination, for example, plus and 0 and so on. For example, let me give you another example of unentangled state. So another example, if I write this state 1 over under 2, 0 1 plus 0 0, can you guess if it is entangled or unentangled state?
Sir, unentangled.
This is unentangled, exactly, because I can write it like this. So this 0 1 is essentially 0 tensor 1. This is just a shorthand for 0 tensor 1, plus this 0 0 is a shorthand for 0 tensor 0. Now I can take this 0 common from left side, and the state of second qubit is 1 plus 0, and this 1 plus 0 is nothing but plus state. So I'm able to describe this joint state as this. And this doesn't have to, have to come to some canonical state that we have studied. This can be anything, but as long as I can separate one qubit from the other qubit, it means it's not an entangled state. But on the other hand, if you look at this state, 0, 0 plus 1, 1, there's no way I can write this state as a product of two individual states of the two qubits. So this is entangled state.
सर आपने जो प्लस स्टेट है यहाँ पे सिर्फ इसको इससे डायरेक्ट लेबल दिया है ना, और इज इट लाइक अ कन्वेंशन टू डू इट लाइक दिस?
I mean, this is conventionally given a label like this, but you can call it whatever you like. It doesn't matter. But that's normally what people call a plus state is this 0 plus 1. So this is in fact, this is the one of the maximally entangled state of two qubit system. We are not going to study in this course, but if you go to full-fledged description of mixed quantum states, where you can have probabilistic mixtures of different states, and then using the density matrix formalism, then we can show that and we can then quantify the degree of entanglement between different systems, and this turns out to be the maximally entangled state, and it actually has a name. It's called Bell state. And this actually, there are 4 maximally entangled state for two qubit system. There is another one. It is 0, 0 minus 1, 1. And then there's another one. It's 0, 1, 0 minus, actually, let me write in standard way. So it's 0, 1 plus 1, 0, and then there's the 4th one, 0, 1 minus 1, 0. So this is, the entangled state, when we can say that this is a state that if qubit 1 is is measured and it turns out to be in state 0, it means the other qubit will also turn out to be in state 1. But if you measure this joint state and the first qubit turns out to be in state 1, the second qubit will also turn out to be in state 1. Because when you do measurement on this entangled state, you either collapse to this state or this state. And if you collapse to this, it means one is in 0 and the other one is in 0. And if you collapse to this state, one is 1 and the other one is 1. The same is the case here. The only difference is that this is a symmetric state and this is anti-symmetric state. That if the first qubit comes out to be 0, the second will come out to be 0 as well. And if the first comes out to be 1, the second will come out to be 1 as well. So these are, they are called entangled for this reason, that the measurement results of both qubits are correlated. That if the first one is 0, the second one is 0 for sure. And if the first one is, we don't know which one the first one is going to turn out, but when we have measured the first qubit, the second qubit state is predetermined, that it's going to be the same as the first one. Over here, it's opposite. If the first turns out to be 0, the second will be 1. Similarly here, but this is symmetric and this is anti-symmetric state. And they have been written in such a way that you can check that all of these 4 states are actually orthogonal to each other. You take, and by the way, we can give them names. For example, this is commonly called 0, 0 state, and this 0, 1 plus 1, 0, this is called 1, 0, and you will see shortly why these states have these names. And this is called 1, 1, and this is called, so this is called 0, 1, and this one is called 1, 1. And so just to distinguish, so we have these 4 Bell states, and they also form an orthonormal basis, because all of these states, they are orthogonal to each other, and they are normalized. So you can express any general state as a superposition of these states. For example, if you have some general state, let's say A, B, C, D, and this is in computational basis. So I can write A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. So this can be, written as a combination, of course, with different weights, that this is 0, 0, some coefficient B prime, 0, 1, some coefficient 1, 0, some coefficient psi 1, 1. And you can find these weights very easily. You substitute for psi 0, 0, for psi 0, 1, for psi 1, 0, psi 1, 1, and then you collect the terms for 0, 0 and equate it to A, and then you collect the terms for 0, 1, equate to B, and you will have 4 equations. You can solve those 4 simultaneous equations, and then you can find this A prime, B prime, C prime, D prime, because we already know A, B, C, D. So we can express any 2-qubit state as a superposition of these Bell states. So they also form an orthonormal basis. Sorry, I think there is a question, but I couldn't hear.
After the Bell states taken, we can also represent them in the plus minus form, or no?
Yes, so we can express them in another basis, which we were calling Hadamard basis. Of course, they will have different weights, but we can express them in plus 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 minus minus plus minus minus basis as well. And if you want to compute these coefficients, it's the same way. You substitute the definition for plus 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 minus minus plus, and then you have a lot of terms that, but you can collect terms that are of 0, 0 type, and their sum would be equal to A. And then you can collect terms of 0, 1 type, and their sum would be B, and you will get 4 equations. And you can solve those 4 equations to find these 4 unknown coefficients for this thing. Okay?
Yes.
Perfect. So any other question about these states? If not, let me now start discussion on 2-qubit gates. And 2-qubit gates are actually, you can say, are at the heart of quantum computation, because they are used to perform joint operations on qubits, and a lot of the applications of quantum computing results from these 2-qubit gates. And fortunately, there are not many 2-qubit gates that you have to work out. Almost all of the 2-qubit gates can be expressed as some 1-qubit gates, and only any 2-qubit gate, or even a higher order qubit gate as well. General qubit gate, they can be expressed as just one type of 2-qubit gate, and some of the single qubit gates like Hadamard and XYZ gates and rotation gates that we will study tomorrow. So, and that the most important qubit gate that everything else can be expressed in terms of, it's called controlled NOT gate, and we will use symbol CX for that. And let me describe it. So X gate that we studied last time, it was like this, that 0 state is transformed to 1, and 1 state is transformed to 0. But this C0 or CX gate is something like this, that you have 2 inputs. One is called the control input, and the other is called the target input. And then at the output also we have control, and you can say the output. So control goes to the output as it is, and the target is changed. So the definition of this gate is like this. If control is 0 and target is 0, you will get control at the output and nothing will happen to target. And if control is 0 and target is 1, nothing happens to control, but nothing happens to target as well. So this control is in 0. So whatever is, target goes to the output. But if control is 1, the X gate is going to be applied to the target qubit, and this will be flipped. So if the target is 1, the target becomes 0. So this is the first time I'm writing these multi-qubit gates. So I'm writing, it like this. But later on, I will be expressing the same thing like this, that CT and, output. So we can write it 0, 0. So 0, 0 goes to 0, 0. So this first one is the control. And 0, 1 goes to 0, 1 again. And 1, 0 goes to 1, 1, because this control is 1. So target 0 is flipped to 1. And 1, 1 state goes to 1, 0, because control is 1. So target is flipped. So this is how, we can express this C0 gate. And it has this symbol. X. One thing you will notice about quantum computing, that the number of inputs and number of outputs are always going to be the same. And this has to do, first of all, with the unitary transformations, because we can have unitary transformations only if the number of inputs and outputs are the same. And it has also to do with the quantum mechanical evolution of state, because all of those unitary transformations are reversible as well. So all of the quantum computing is reversible. And to have reversible computation, we have to make sure the number of inputs are equal to number of outputs, because if number of outputs are decreased, like in classical computation, where you are familiar with the lot of gates of like these, for example, XOR gate is like this, that you go from 2 input to 1 input. But in quantum computing, number of inputs and number of outputs will always be the same. This, by the way, control NOT gate is sometimes also called the equivalent of classical XOR, with the addition that this one input is also available at the output, because this output that you see is just the XOR of these control and target. For example, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 modulo 2 is 0, because 1 plus 1 will become 2, and if you take modulo 2, 2 divided by 2 will give remainder 0, so you get 0 here. So this is a modulo 2 XOR sort of gate. So that's why sometime we would write it's, so control goes to the output, and target can be written as C plus T if so we don't actually have to write any if. So this the output of this is this XOR operation of control and target. Perfect. So any question about control NOT gate? Now, let me express this control NOT gate in 2 forms. So let's first do in matrix form. So in matrix form, you see, nothing is happening to this qubit, and X gate is happening to the second qubit. So this CX can be written as identity tensors X, because identity is happening to this qubit 1 and X is happening on the qubit 2. So identity is 1, 0, 0, 1 tensor, and X is 0, 1, 1, 0. And if you use the rules of tensor product, so this 1 will multiply 0, 1, 1, 0. So I will get 0, 1, 1, 0. This 0 will multiply 0, 1. So I get 0, 0, 0, 0. This 0 multiplies all 0, 0, 0, 0. This 1 multiplies this. So I get 0, 1, 1, 0. So this is, the matrix form of this operator. But I can also get, an operator form. Now, to get its operator form, I will have to work out these things. To get operator form, there are two ways. And let me first do it the hard way, and then I will do it, the simpler way that most of the time we will be doing later. The hard way is this, that we have, this basis state. So our basis is 0, 0, 0, 1, 1, 0, 1, 1. So I will have to work out these outer products like 0, 0, 0, 0 outer product is 1, 0, 0, 0. Sorry, not tensor, but the outer product. So this 0, 0 is 1, 0, 0, and then 0, 0 is 1, 0, 0, 0. So this becomes 1 into 1 is 1, and then all others are 0. Okay, similarly, then I will have to work out 0, 0, 0, 1. So this is 0, 1, and the 1 comes here. So this will be 0, 1, 0, 0, 0, 0. And you get the point, okay? I will have to work out 16 outer products of, all possible combinations of these states. And then I see, okay, this term corresponds to this term, and this corresponds to 0, 1 into 0, 0. Similarly, this will correspond to something, this will correspond to something, and then I will be able to express it in the outer product form. But there is a simple way. If you remember that these are, the orthogonal states, which mean that 0, 0 inner product with any of the other three will give me 0. And 0, 0 will give me 1 only when it is inner product with itself. So, and we have to go back to the truth table, which is given right here. And let me see what our outer product form of this, operator should look like. It should transform 0, 0 state to 0, 0. 0, 1 should transform to 0, 1. And 1, 0 should transform to 1, 1. And 1, 1 should transform to 1, 0. So it means I can express this operator Cx in outer product form like this. Because 0, 0 had to go to 0, 0. So it means there should be a term like this, because when 0, 0 comes from right, this will be dot product with that and give me 1, and I'll get 0, 0. And also 0, 1 should come to 0, 1. So I should have another term like this. This is a little bit bigger. Plus, no, the 1, 0 should transform to 1, 1. And similarly, 1, 1 I'm trying to erase. Let's see. Okay. All right. So 1, 1 1, apologies. Okay. 1, 1, 1 should go to 1, 0. So it means this is the operator form of my operator, which you could have gotten by doing all of these outer products and then decomposing this bigger matrix, and realizing that okay, this is so this is the 0 1 and 0 1 terms, and 1 1 1 and 1 0, etc. So we can skip that part and write the operator form directly from this truth table, because we have to make sure that 0 0 goes to 0 0 and etc. So whatever state you want to transform to the other one, it should come on the right side, and the state that you want to get corresponding to that should come on the left side. And we can now check by doing a couple of things. For example, if you want to see that what would you get if you apply your CX to plus plus state. Okay, and we can write it like this: 0 0 0 0 plus 0 1 0 1 1 1 1 0 plus 1 0 1 1. Actually, this is going to be a little bit complicated, so let me write it as a state 1 1. So 1 1 comes here, because if I write plus plus, there are going to be 4 terms over there. So now when this 1 1 is in a product with this one, it will give me 1, and I will get 1 0. But when this 1 1 is multiplying with 1 0 or 0 1 or 0 0, we'll get 0. So the result is 1 0. So this is the usefulness of this operator form, that we can quickly work out the outputs for any inputs. But fortunately, we won't be doing too much analytical work, so you wouldn't have to worry about working with these equations too much. But this is helpful when we are trying to understand or build or analyze algorithms. Okay, any questions about it so far? Perfect. So let me introduce another gate, and this is called controlled Z gate. Now, controlled Z gate is like this, that this is its symbol. And actually, we'll see, a little bit later that even though this was a symbol initially, but some people would actually use this symbol as well. So this is target. So the idea is this, that if control is 0, nothing happened to target. So 0 0 goes to 0 0, and 0 1 goes to 0 1. But if control is 1, the target gets a phase if target is 1, because Z gate, if you remember, was this. Z was 1 0 0 minus 1. Then it gives a phase if the input is qubit 1 in one state. So if target is 1 and if control is 1 and target is 0, we get 1 0 out again. But if target is 1 and control is 1, so it means we get a minus sign with the target. And since you can see the symmetry over here, that you get a minus sign only if both of your inputs are 1, and if any one of the input is 0 or 1, you don't get minus sign, you get the same output. So then it doesn't matter which one is control and which one is target. So that's why it is a symmetric gate. So it also have this symmetric notation that some people use it. And I'm sure you can quickly see that you can represent in operator form very easily, that 0 0 is going to 0 0, 0 1 is going to 0 1, 1 0 is going to 1 0, and only 1 1 is going to 1 1. So with this operator form, we can write it like this. Okay, so any question with this? Now, we can actually construct this control Z gate from control X gate as well. And the reason is this, that we can, we can perform this, we can construct an X gate from Hadamard and Z and Hadamard. For example, in today's activity, you're going to show this thing, that X gate is equal to actually Hadamard Z into Hadamard, which means that if I have an X gate like this, and it is a control gate, but before that I have a Hadamard and I have a Hadamard later on, this is essentially nothing but a control Z gate, because this Hadamard X Hadamard is basically okay. So let me put an X here and Z here. So I can make this control Z gate in terms of control X gate. Similarly, other gates, many other gates, we can construct using control X gates. In general, we can define the control operation as control unitary. So a control unitary is a gate like this. It has this symbol, which means that if your control is 0, nothing happens to target. But if your control is 1, target is applied with this, unitary gate. And in general, we can construct this unitary gate using control X gate once we know what the form of unitary gate is, and using maybe one or more control X gates, we can construct this control unitary operations. We will do it when we get to a situation where we actually have to find it out. Okay, so let me pause here for a question. If not, let's move on and now start using these circuits to do something useful. And let me begin with constructing an algorithm. The first algorithm perhaps of this course, and sometime we will call algorithm by the name circuits, because we are using circuit model to express algorithm for preparing Bell state. So our goal is that we want to prepare these Bell state. 0 0 was 0 0 plus 1 1 and so on. Okay, and let me give the circuit first and then show that it really does what we are saying that it does. And the circuit is simple, and it's given by this. You have two qubits, let's call it I, and the second qubit, let's call it J. You Hadamard the first qubit, and then you do a controlled X, and then this circuit we claim prepares this Bell state. And let's see how. Suppose your I state is 0 and your J state is 0. So over here we are at 0 0 phase. So what happens when we are at this stage? At this stage, let me call it some psi 1. So psi 1, and let me label it with 0 0, is Hadamard performed on the first zero and identity performed on the second zero, because nothing is happening here and Hadamard is happening here. So this becomes the plus gate, which is 1 over square root 2, 0 plus 1, and nothing happens to the second qubit. Now, what is the output after the CX operation? So let me call it psi 2 0 0, and this is after CX applied to this psi 1 0 0 state. And when we do CX, so we have to apply CX to 0 0 plus 1 0. So when CX is applied to this thing, control is 0 and target is 0. So we get the same state. Because control is 0, nothing happens to the target. But for the second one, when control is 1, so target is flipped. So we get 1 1 state. And you can see that this is nothing but the psi 0 0 Bell state. So what we did with this circuit, we started from the unentangled state 0 0, and by applying the Hadamard and doing a conditional X gate on the second qubit with respect to the first one, and we arrived at the entangled state. And now you can see how the entanglement is being generated. That if your control bit is in a superposition state, as it was the case here, so this was the superposition state that we were able to prepare after performing Hadamard on 0 state. When we perform Hadamard to 0, we get to this plus state, which is the superposition of 0 and 1. And when we apply the X gate conditioned on this superposition state, because this is 0 plus 1, so once nothing happens to this second bit, and for the second part of the superposition bit, this 0 is flipped to 1. And so now this is a joint state of these two qubits that we cannot express as the product of the first and second one. So this is how this Bell state is prepared, and now you can see why there is this label 0 0, because this state can be prepared with this circuit by starting from this 0 0 input state. And I leave it to you to check that. Similarly, if our input is 0 1, we will arrive at 0. Let me see what will be the state for 0 1. We will arrive at 0 1 plus 1 0 state. Similarly, if our input is psi 1 0, we will arrive at 0 0 minus 1 1. And if our input is 1 1, we will arrive at the fourth Bell state, 0 1 minus 1 0. So we can prepare these 4 Bell states, and in the lab session today, I will be implementing this circuit and showing you how this superposition state is being prepared. So any question on the preparation of Bell state circuit or algorithm? Okay, so if not, let me go on to the next part, which is how can we measure the presence of entanglement in our state. Suppose you are given some state psi, let's say A 0 0 plus B 0 1 plus C 1 0 plus D 1 1. So it's something coming out to you from some communication channel, or from some part, and I mean quantum communication channel, or at some part in your quantum computing stage, that you have some state psi, and you want to measure the presence of these Bell states in your circuit, that how much of this is present and how much of this is present, and this and so on. So essentially, I want to measure the presence of these Bell states in this input state. So it is the technical word for it is it's called measuring in Bell basis. So the circuit for that is actually just the inverse of the entanglement circuit. So we do inverse operation. We do first CX, and then we do Hadamard on this qubit, and we go here. And the idea is this, that since this state can be written as any general state, A prime some psi 00 plus some B prime psi 01 plus some C prime psi 10 plus some D prime psi 11. So I can express the same state, as a linear combination of these 4 Bell states. But the trouble is that whenever we do the measurements are usually performed in computational basis as well. So if you have this psi, and even though mathematically you can represent it like this, but if you do measurement, you will again measure only A, B, C, and D. I mean, the probability is proportional to A, B, C, D, because you either measure 0, 0, or you measure 0, 1, or you measure 1, 0, and so on, and then you keep counting, and at the end you have probabilities that are proportional to A mod square, B mod square, C mod square, and D square. So I will have to do something on this, state, that where I'm finding this psi 0, 0, this psi 0, 0 is replaced by 0, 0. So this circuit can do that, because if I have some psi ij state as input here, so this is just the inverse of entangling circuit. So it means if input is psi ij, the output would be I here and j here. So when this general state passes through this circuit, this will be transformed to a state like this: psi A prime 0, 0, B prime 0, 1, C prime 1, 0, D prime 1, 1. And now when we do measurement over here, and measurement is always in computational basis. So after this transformation of my state psi to some state psi prime, I have changed these Bell states to 0, 0, 0, 1, etc. So now when my measurement will generate a histogram like this, that it will measure, let's say, 0, 0 state with some frequency, and 0, 1 with something, and maybe 1, 0 with something, and 1, 1 with something. Now these coefficients will be proportional to A prime square, this will be proportional to B prime square, and this will be proportional to C prime square, and this will be proportional to D prime square. So by the relative height of these histograms, I'll be able to find out what A prime, B prime, C prime, D prime is, or in other way, I will be able to find out how much of psi 0, 0, psi 0, 1, etc. is present. Okay, so to summarize, if we have a state in computational basis state, mathematically, I can express it, in other bases as well. But if I just start measuring over here, then again, I will measure only A, B, C, D. But if I transform my state in such a way that this basis is transformed to 0, 0, 0, 1, etc. So for example, if it is, Bell basis, I can do this inverse Bell, and then I do measurements over here, then my coefficients would represent the weights of these new bases. Any questions? Okay, I hope that you can now understand that if you want to measure in Hadamard basis, that you want to find out what are the weights in this basis, all you have to do is just Hadamard the input, because these Hadamard transform, this transform plus to 0 and minus to 1, and similarly, this one, that after this Hadamard transform, this psi will be converted to 0, 0, and so on. And if you do measurement now over here, this is, by the way, the symbol for measurement. And after measurement, we put 2 lines to indicate that this was the quantum qubit, and this is the classical qubit, 2 line. Anyway, so if we now do measurement of these Hadamard transforms, we will measure the weights of these plus, 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 minus, etc. states. So this is how we can measure in different bases. Mostly we will be measuring in computational basis, so we won't be doing any transform. But if you know, especially when we talk about quantum communication, quantum secure communication, then people have device schemes that they secretly, prepare signals and messages in certain bases, and or maybe a random selection of bases, either sometime Hadamard, sometime Bell bases, etc. And then they're able to encode their message in a better way and reduce the probability of error. But when we talk about quantum computing, most of the time we would be, working in computational basis and not changing the basis. Okay, so any question? All right, so let me, do one last thing using quantum, using the control NOT gate, and then we will go on to our lab session. And this is actually one of the widely applicable topic in quantum algorithms that we will need later on. And this is, this has a technical name. It's called phase kickback. And you will see, the reason for this name. So let me get back to, this control X gate. And when anyone, think of this controlled X gate first time, they picture it, like this. That control remains the same. Nothing happens to the control, and target, is XORed with the control. And we get, we can get entanglement and so on. But we can, prepare our controls and targets in certain ways that we can actually have a phase which is present as a global phase. So if we are able to, set our target in certain way that the total phase that is applied to the circuit is a global phase, then by having, different superpositions of these controlled inputs, we can get, phases at different for different combinations of inputs. And let me, describe it how. If you prepare your target state in this minus state, and minus state is just an abbreviation for this thing. So let's see what happens if the target is set in this minus state. So if control is 0, then the X gate will not be applied to the target because target remain as it is. But if control is 1, then X gate is applied to the target, which is X. This becomes 1 over square root 2, and I can write 0 first and 1 later. And this is nothing but minus state again. So what happens that when control is 1, a negative sign appears in front of minus state. So it means that when you have control 0 and target in minus state, you get the same state at the output. But if control is in one state and target is in negative state, you get a minus sign. And this minus sign appears in front of this joint state, which means that we can think of this phase present either with the target or with the control. And sorry, this 0 has to be 1. So this minus sign, because I can write it like minus 1 tensor minus, or I can write it 1 tensor minus. So this minus can be, thought of appearing in front of any state, because this is a global phase now. It's multiplying these two states. So it means that if I have a circuit like this, suppose there are two inputs, and I have one controlled not over here and nothing happening here. So this is my qubit 1, qubit 2, and let's just say qubit 0 and qubit 1, because indexing in Python starts from 0. And this qubit is fixed in minus state. Now let's prepare the table. What happens when qubit 0 is in 0 state and qubit 1 is in 0 state? So if it is 0, nothing happens here, you get output 0, 0. So this is output. If qubit 0 is in 0 state, but qubit 1 is now in 1 state. So this is 1. So this means that we will get, let me make it like this. So we will get 0, 1. Because this, because of this, target state in minus state, there will be a minus sign appearing. And if the qubit 0 is in 1 state and this is 0, so we will get again 1, 0. So I'm now talking about output here. Okay. And this is minus state, this will remain minus state. So nothing is happening to this qubit. And if it is 1, 1, and since this is the second qubit, so I get a minus sign again. So it means by putting this this third qubit in minus state, I can prepare the first two qubit in such a way that I can get minus sign in front of half of them and plus sign in front of the other half of them, which means that, for example, for this case, I can say that my qubit Q0, Q1 is transformed to minus 1 raised to power Q1, Q0, Q1. Because when Q1 is 1, I see when Q1 is 1, a minus sign is appearing, which is equivalent to saying minus 1 raised to power 1. And when Q1 is 0, minus 1 power raised to power 0 is plus. So the state remains plus. So I have been sort of, able to implement a certain function. In this case, that function of Q0, Q1 is just Q1. And I have been able to implement this function of minus 1 raised to power this function. So this is called, the implementation of function in the phase of minus 1 raised to power something. You can, devise different functions. For example, if you put a Q0 again with respect to the second qubit as well, you can see that 0, 0 will transform to 0, 0, because a minus sign will appear from this CX and minus sign from this CX, and minus into minus is plus. But 1, 0 will go to minus 1, 0, and 0, 1 will go to minus 0, 1, but 1, 1 will go to plus 1, 1, right? Because when it is 1, 1, they will both be acting on it, and minus minus will give me plus. So now I'm getting minus sign for two different things. And actually this is nothing but -1 raised to power Q0 plus Q1. Because when either of them is 1 and the other is 0, I'm getting a minus sign. And when they're both either 0 or 1, I'm getting plus state. So 1 plus 1 is 2, and -1 raised to power 2 is plus again. So in this case, when I have two C naughts, I have been able to implement functions like Q0 plus Q1. So sorry, F is just Q0 plus Q1. Similarly, you can implement different functions. For example, if I have this qubit doing nothing, but on this qubit, I first do an X gate, and I do an X gate again, and I now do a control X over here, and this is again in the minus state and remains in minus state. So let's say this is Q0, this is Q1, and you can guess that over here you are getting Q0, Q1 as it is, because I did an X gate over here, performed a CX with respect to this, but then flipped it again. So I can now implement again another function F that my Q0, Q1 will go to -1 raised to power F, but now with the different functions. Okay. This, by the way, is called ancilla bit. If you know it's doing nothing in a sense that it is in minus state, remains in minus state, but these bits are changing, that their phase is changing. Okay, so is there any question? Okay, so if there are no questions, let me close this session, and we will meet after 10 minutes for the lab session.